Hi, everyone. I'm Fedor, a postdoc at Caltech, and this is a joint work with Alexander Kolesnikov from HSE, Aleh Tsyvinski from Yale, and Alexander Zimin, who is now a grad student at MIT. And according to my knowledge, none of us are specialists in auction theory, so it's our first paper on auctions. And this is why I'm especially excited to present this paper here, and I'm grateful to Itai, Sasha, and Alex for this opportunity. So in this paper, we ask a very basic question: what is the most profitable way to sell M unrelated items to N agents? And to be precise, we consider Bayesian setting. So our agents have independent private values over the goods, and the seller knows the distribution, and the fact that our items are unrelated is captured by the fact that their utilities are additive. So what's the most profitable mechanism to sell the goods? So what's known about this problem? Of course, if there is just one good, the answer is classic. It is given by Meyerson. We just need to use second price auction with a reserve or any other efficient auction mechanism. Surprisingly, even if we have just one agent, one buyer, but several goods, the problem becomes extremely complicated. And this is the so-called multi-item or multi-good monopolist problem. So optimal mechanisms in these settings are known only for a few particular cases. And there was a breakthrough by Daskalakis, Deckelbaum, and Zamos, who developed a dual approach to this problem, connecting it to optimal transportation. And in particular, their approach was able to kind of unify, to give a general umbrella framework, the general technique to obtain previously known sporadic results. What about the case of several bidders and several items? Essentially, nothing is known about optimal mechanisms in this case, even though, of course, in practice, there are some mechanisms that work pretty well, like simultaneous ascending auctions. But we do not know what's the optimal mechanism. What is the mechanism maximizing the revenue? And in particular, a connection to optimal transportation, the very existence of this connection was an open problem. And in our paper, we show that actually these multi-agent, multi-item auctions, they reduce to a certain problem of optimal transportation, but there are some surprises along this way. First of all, why we're interested in this question? Because for practice, maybe we do not really need to know what's the optimal mechanism if there are mechanisms that work well. The reason we are interested in this problem is because this is kind of a benchmark setting combining obstacles of multidimensional mechanism design and multi-agent mechanism design, which in the end results in problems of multidimensional majorization. And majorization techniques are now is a cutting edge in many sub-areas of mechanism design, but multidimensional majorization is something that is not yet well understood. So what we will see? We will see the following result, the following strong duality. So for any number of bidders and with additive utilities, any distribution and any number of items, the maximal revenue that we can achieve in Bayesian incentive-compatible individually rational mechanism is equal to the minimal cost of a certain transportation flow. So, I will give you a formal statement later. And I guess the left-hand side of this identity is intuitive. And so let's discuss what is this animal on the right-hand side. What is this transportation problem? So what optimal transportation is about? We're given some set X, which is thought as a set of geographic locations. And we have production and consumption of a certain commodity that are spread over this set. And production, the measure P plus corresponding to production is not equal to the measure P1, P minus corresponding to consumption. And so the produced commodity must be transported to satisfy the demand. And the general idea behind the transportation problem is that we want to find the cheapest way to transport. OK. So I guess many of you have heard about optimal transportation, but most likely you've heard about the so-called Monch-Kantorovich problem. So what is this problem? You are given these measures P plus and P minus, and you are given a cost function that C of xy. So it depends on the two locations. And the goal is to find a distribution on x times x, a distribution gamma, that has this P plus and P minus as marginals and minimizes the expected cost. So this gamma is thought as a transportation plan. So it determines how the commodity produced at a particular point, where it is transported. So if we drop this transportation framing, this is an archetypal coupling problem. So we're given two random variables with distributions P plus and P minus, and we want to find a joint distribution of these random variables that maximizes, that optimizes a certain objective. And this is the reason why this problem, Monch-Kantorovich problem, is omnipresent in economic and statistical applications. Because, for example, in many questions of mechanism design, what we want to couple the realization of agents types with a certain decision. And this is an archetypal problem of finding the optimal coupling. In particular, this is exactly the transportation problem that appears in the results by Daskalakis and others in the case of one bidder. And one thing to note about this problem is that transportation somehow happens momentarily. So we do not keep track of the trajectory, but we just specify for each x, we specify point y where this x is transported. And there is another transportation problem, Beckmann's transportation problem, which is apparently less known, even though it was introduced by an economist, Martin Beckmann, and the paper is published in Econometrica 1952. So Beckmann was interested in modeling transportation flows, but he presumably did not know about already existed a theory by Monch and Kantorovich, and he came up with another way to formalize the idea of transportation. which is also more than reasonable, but it is slightly different. So again, we are given this p plus and p minus, and we're given a certain cost function phi that depends just on one vector argument. And now our goal is to find a transportation flow with the minimal cost. So the idea is the following. We have our set X of geographic locations, and at each point of this set, we have a vector field whose direction and magnitude correspond to the direction and the intensity of transportation in this particular point. And this vector field satisfies the following requirements. If we take a subset, a certain subset A of our space, then the difference between inflow and outflow must be equal to the difference between demand and supply in this region A. And by the Gauss theorem, the difference between inflow and outflow is the integral of the divergence of our vector field F over the set A. And so we want this to be equal to P plus of A minus P minus of A. And we want this identity hold for any good subset A. So in other words, it means that the integrands are equal, so the divergence of F is equal to the difference between supply and demand. And so the problem takes the following form. We want to minimize the cost over all vector fields F that satisfy the condition that their divergence is equal to P plus minus P minus. And the cost at a point X is given by this phi, function phi, of the vector field at this point. So now transportation is continuous. We keep track of the trajectories. And what is surprising is that as a dual to this multi-item auction design problem, we get Beckmann's optimal transportation and not the one by Monge and Kantorovich. So in the interest of time, I will be very brief regarding the related literature, but I can come back to it during Q&A. What I want to mention is that, as I said, there are multiple applications of Monge-Kantorovich transportation in economics, but there are just a few appearances of Beckmann's problem. So there are recent papers by Feigelbaum and Schall, and also Aleh and Arkalakis. And in their papers, Beckmann's problem appears to capture spatial equilibrium. And in a series of works by Sant'Ambrogio, it appears as a mean field limit of Ward-Drop equilibria in some transportation networks. So before our paper, Beckmann's problem has appeared only in those contexts that are literally intended to model the transportation issues. So our paper is the first appearance of Beckmann's problem is in non-transportation context. And also, I want to mention that from technical perspective, our paper is a part of the growing literature on majorization techniques in economics. OK. So what is my plan for the rest of the talk? I want to show you, even though it's a bit of a detour, I want to start with the known result for the case of one bidder, because it will be easier to illustrate what breaks down when we try to attack the case of several bidders, and also will prepare us for the formal statement of our main result. And in the end of the talk, we'll talk a little bit about applications and simulations. So let me skip the case of one bidder. OK, so the case of one bidder and several goods. We have an agent whose values are sorry. We have an agent, and she has a vector of values for each of the goods, and this vector comes from some distribution rho. Our agent has additive utilities over the goods. So if she gets a bundle X and pays T to the auctioneer, her utility is the scalar product X and V minus T. OK, yeah, it seemed that I uploaded the extended version of the slide, so let me go fast here. So we want to maximize the seller's revenue over BIC individually rational mechanisms, and of course there are some simple ideas of what should we do. We can try selling items separately. We can try selling the grand bundle. But it turns out that none of these natural ideas give us an optimal mechanism. At least there are distributions for which it's not optimal, even if values are not, even if the values over the goods are independent. And by the revelation principle, we can think of menu mechanisms. So we offer a certain bundle and put a price on it. We offer another bundle and put a price on it, or we allow for paying 0 and getting 0. By revelation principle, any Bayesian incentive compatible mechanism is equivalent to offering our agent such a menu, and our agent will choose the best item from this menu. But of course, maximization of such menus is not a very tractable problem. And we also know that actually we need to sell fractional bundles from time to time. So the optimum is not achieved on selling each item deterministically, but sometimes we need to randomize. And the idea is that instead of maximizing over menus, we can maximize over the utility functions. This idea comes, I think it comes from Rocher and Chonet. So for each menu, we can introduce an interim utility function of an agent. So this is just the utility that our agent with type V has when faces this mechanism. So our agent picks the best item from the menu, and this is the utility as she gets. It's easy to see that this function is convex, just because it's a maximum over linear functions. And also, it turns out that given this function, you can actually reconstruct the mechanism. So the allocation x is given by the gradient of this function u, and you can also reconstruct the payment. So you can assign a utility function to a mechanism, but you can also do other way around. You can deduce the mechanism given the utility function. And there is a theorem by Rocher-Chonet that actually this correspondence is one-to-one. So for any BIC incentive, BIC individually rational mechanism, you can assign the utility function and vice versa. And the class of utility functions that you get are convex functions u that are 0 at 0, and whose gradient belongs to the m-dimensional unit cube. This condition corresponds to the fact that the allocation is given by some vector in the unit cube, and we know that this gradient is the allocation x. Given this observation, Rocher and Chanet represented the problem of revenue maximization the following way. So we want to maximize this integral objective over all convex functions u that are 0 at 0 and that have gradient in the m-dimensional unit cube. Actually, this objective can be simplified a little bit. We can get rid of derivatives in the integral. So this is the objective. We can integrate by parts. Again, I do not go into any technicalities. So we assume that the contribution of the boundary when we integrate by parts is 0. And we get that essentially our objective is just the integral of u with respect to some measure psi, the so-called transfer measure. One thing to keep in mind is that this psi is not necessarily a positive measure, so it may have positive and negative parts. OK, so selling m items to one agent corresponds to this pretty neat optimization problem. And so Daskalakis and others asked what's its dual. And to formulate what is the dual, we need the concept of second-order stochastic dominance. So for two measures, mu and nu, we say that mu second-order stochastically dominates nu. If for any convex monotone g, integral of g with respect to mu is greater or equal than the integral of g with respect to nu. And this notion is also applicable to signed measures, so mu and nu are not necessary probability measures. And so what Daskalakis and others obtained is that the dual problem is the following problem of optimal transportation. There is one twist compared to Monch-Kantorovich. So here the two marginals are not fixed, but the marginals gamma 1 and gamma 2 are such that their difference is required to dominate in this in the second order stochastic in the sense of second order stochastic dominance. This difference must dominate this transfer measure psi that enters our objective. And up to this twist, it's just the Monch-Kantorovich transportation problem where the cost is given by the L1 distance between the 2 points. So it's a Monch-Kantorovich problem with majorization. OK, so let's now think what we can do in the case of several bidders. So again, we want to maximize the revenue of Bayesian incentive-compatible individually rational mechanisms. And to some extent, we want to use the same approach. And to some extent, we can do that. In particular, even if you have a multi-agent mechanism, you can look at its reduced form. So for each agent, you look at how her expected allocation depends on her own report. So we average over the realization of types of all our other agents. And as before, these reduced mechanisms can be represented by interim utility functions. So they correspond to convex functions u with the requirements that we discussed before. But there is one obstacle. We get a new feasibility constraint. So not every function u corresponds to a symmetric and agent mechanism. And it turns out that this feasibility constraint again boils down to the property of second-order stochastic dominance. So it turns out that it takes the following form. So each component of the gradient of u must be dominated by z to n minus 1, where z is uniformly distributed on 0, 1. And the gradient is considered to be a random variable because v, agent's type, is distributed according to rho. So this feasibility constraint in this form was proved by Hart and Rennie in the case of one item. So we observed that actually exactly the same result holds in the case of multiple items, but you need to apply it to all the components of the gradient. And this corresponds to a more known earlier result by Kim Boulder characterizing reduced form mechanisms. OK, so this is how the primal problem looks like. So it looks almost the same as before, but now instead of the condition that the gradient must belong to the m-dimensional unit cube, we have this dominance condition on the gradients distribution. And it's a major obstacle because it restricts the distribution of the gradient. So it's a non-local condition. So how the dual looks like. Just recalling you how the Beckmann's transportation problem looks like, but here there is one nuance. Now the density rho also enters this Beckmann's problem. So as you see, it enters the divergence, and it also enters the cost function. So what are the costs? The costs are endogenous. So consider a collection of convex monotone functions phi I on R plus that are 0 at 0. And it turns out that we need a cost that is defined the following way. So it's phi of f is a separable cost where phi I star are Fenchel conjugates of these functions phi I. Yeah, I understand that there are many layers in this construction, but I think this is the last one. And so this is how the dual problem looks like. So similarly to what we saw in the case of problem by Daskalakis, we minimize over similarly to that problem, we have the majorization constraint. So we minimize over distributions phi that second order stochastically dominate measure psi, this transform measure. And we also minimize over functions phi I. And in the objective, we have Beckmann's problem and an extra penalizing term. So this term does not allow us to select phi I to be big enough. And when we select phi I big enough, then the cost in Beckmann's problem decreases. So there is a competition between these two terms. OK, in the interest of time, I will need to skip this discussion. One thing that I want to mention, in the case of one agent, we get two dual problems. We get the problem by the representation by Daskalakis and ours. But how can it be that a problem has two duals? They must be somehow related. It turns out that in the case of one agent, these are different slides. Yeah, so in the case of one agent, this Beckmann's problem can be simplified And so in the objective, we just get Beckmann's problem with L1 distance. And there is a theorem by Sant'Ambrogio which tells that for these particular cases, the cost is given by L1 distance. Beckmann's problem coincides with a problem by Monch-Kantorovich. And as a result, this theorem implies that we get the result by Daskalakis and others as a corollary of our theorem. OK, so I think it's more or less time for me to stop. Let me stop on some nice figures. OK, maybe I need to mention one more thing. So how can we use this duality? First of all, we can use it to disprove that something is optimal by looking at complementary slackness conditions. And in particular, we can show that selling separately using optimal Myersonian auctions for each of the items is never optimal for any continuous distribution. Also, we are able to use our technique to recover some known results in the case of one bidder. And of course, the interesting question is whether it's possible to describe, to find an explicit solution to a multi-bidder, multi-item auction. And despite our substantial effort, we did not find such a solution. And there is a suspicion that it does not exist, even in the case of two uniform items and two agents. So this is the result of our computation. So even though this picture looks like it has some flat regions, so this graph is a graph of the probability to get the first item as a function of the values for the first and the second item. Even though it looks like there are some flat regions, actually there are not, and we try to fit various explicit functions to approximate this graph, and it doesn't work. There are some algorithmic insights behind these simulations, but I'm out of time. Thank you.
Hello, thanks for the exciting talk. I would have two questions. One is, can anything be said about nonlinear utilities? So I guess if you use convex ones, then your proof goes through.
Do you mean convex utilities instead of additive ones?
You had that the utility of an agent is linear, x, the scalar product of xd.
Yeah. Not sure. So I think what is important is homotheticity. So like maybe if your items are perfect complements and your utility is just minimum of the utilities over the items, then maybe you can apply similar techniques, even though we haven't tried. And if you have nonlinearity, I doubt it.
Okay, quick second questions regarding your experimental simulations. So if I remember correctly, that paper by Dütting and Aleh also had simulations with DNNs. How do you compare to that?
They are similar, but our simulations are of much higher quality because what they did, they used deep neural networks. So they just formulate the auction design problem as a huge LP, which is completely untractable for the usual LP solvers. They feed it to deep neural network, and still this network manages to approximate the solution quite well. What we do, we first of all rely on multi to single agent reduction, and there are also some optimizations using optimal transportation insights. And in the end, we can feed the problem to a usual LP solver. So you do not need deep neural networks, and even using this usual LP solver, you get higher quality of simulation. So in our comparing our pictures with what they get, we see that in their simulations you have some smoothing artifacts. And here you have these regions where you can identify the regions where, for example, this almost linear part of the solution changes the regime. So in particular, you see this nonlinear reserve price in this picture.
Okay, so you get different results for the settings where the optimal mechanism is not known.
It is similar. It's kind of much higher resolution compared to what they get. But it is possible to combine our approach and put deep neural networks on top, and that would be, I think, the best you can do for automated mechanism design.
Thank you very much.
Okay, so thank you. Thank you, the speakers. And we will be, have lunch now, and we'll be back at 1:30. Yes. Okay.